Hello everyone. Hey guys, I welcome you all for this session, and today we are going to have a class over the resonance, a game changer. You might all know what is resonance, right? That is the delocalization of pi electrons, but yet this topic is very important and it is a game changer. I am going to tell you that how resonance is a game changer. The 5 points where we get our answers wrong because we actually don't know about the game changing of resonance. Okay, so I hope you all are very excited to know all those 5 points where a resonance becomes a game changer. So I want all of you to join me for this session live. As you might all know, this is a live session. Okay, I can see being genius. Hello bache, I hope many of you will keep joining me for this class, which is going to be of approximately half an hour. Okay, yeah, that much time is like much sufficient for us to know all the things all together. Let's begin with it, guys. So the first thing first, resonance increases the stability. Increases the stability. So what does this mean? Before I tell you about more on this topic, guys, first of all, anybody of you who are even in class 11th, 12th or a dropper, or for any other competitive exams, if you are like learning, if you don't know about all those 5 points about the resonance, then this is a must watch for you, all of you. The very first point is resonance increases the stability. You all know resonance is an exothermic process. Resonance is an exothermic process. So if this is an exothermic process, whenever the resonance occurs, there is a release of energy. For an exothermic process, there we will be having a release of energy. When there will be a release of energy, the energy slows down. Okay, when any of the structure gets into its lower energy state, it becomes more stable. So resonance, we need to know that resonance, whenever there is a delocalization of electron, it leads to more stability. Okay, so basically any of the molecule, we can say that molecules exhibiting resonance gets more stabilized. So here I will be giving you an example to understand the whole point. Example, if you will be comparing between CH3NO2, okay, so this is one of the molecule, and you have a CH2 negative NO2. So if you will see these two molecules, okay, so what you can observe is here, because of this negative charge, we will be having the delocalization of electron. Okay, and because of this delocalization of electron, this negative, this NO2 will undergo delocalization, and because of this reason, this NO2 molecule with this carbon is much more stabilized. Okay, though here in this molecule there is no such resonance. We could have many other examples. If we will be looking for this as a molecule, that is CH3, CH2, 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 single bond C, double bond OH. So this is a molecule which I am having. If let's say I put a double bond here, okay, let's say if I put a double bond here, then what will happen? Let me remove all these two hydrogens. So this is one of the structure, okay, and the another structure is, this is the structure number A, this is the structure number B. Now again, this is the example number 2, and here in the example number 2, this is the structure number A, and the structure number 2 is this. See, What is the difference between the two structures? Here also we are having 5 carbons, here also we are having 5 carbons. But here if you would see, here this pi bond will undergo delocalization. Sorry, I did a mistake. What I want to show is basically something different. So yeah, if I put a double bond here and this is CH2 and this has to be CH. Yeah, now it's a right structure. So if in this particular structure, if you would see, this pi bond and this pi bond are undergoing delocalization. This can go here, this can go here. Okay, so we are having a delocalization of electron. There is a resonance. So because of this resonance, this particular structure is much more stable. Okay, this structure is much more stable than this. Why? Because here also we have a pi bond, but are they in conjugation? No, they are not in conjugation. So for the resonance to occur, what is the necessary condition? The necessary condition is that you must be having X, double bond Y, single bond Z. Over this particular Z, you must be having something like a negative charge, a positive charge, a pi bond, or any other vacant orbital or something. Then only the resonance occur. But here if you would see, this is X, this is Y and this is Z, and over this particular Z, yes, we have a pi bond. So this pi bond is undergoing delocalization. I can even put one more pi bond. Yeah, I can show that there is there is a linear conjugation. So obviously the structure number A is much more stable than the structure number B. Okay, and here if you will see in the example number 1, we can see that the structure number 2 is much more stable than the structure number A. Though it is a charged species, but still this is more stable because here we have a resonance, but here we don't have any resonance. Okay, so yes, more resonance. It doesn't mean more resonance, more stability. Pura resonance means stability. Okay, now if you want to see the stability in the resonating structures, you need to watch my previous lecture where I discussed with you what are the factors that leads to the stability. Okay, it doesn't mean that more number of resonating structures, more will be the stability. There are other factors like a molecule has to be neutral with the complete octet, a molecule has to have a more number of bond orders or more number of covalent bonds, or we can say that if it's a charged structure, then the charges must be closer, opposite charges must be closer, and the like charges has to be away from each other, so for the more stability. Okay, so on the basis of the number of resonating structures, we can't say that there will be more stability. Resonance itself is an exothermic process that leads to stability, but to understand the resonance stability, you need to watch my another lecture. Okay, there are many other factors. There are 7 factors which decides the stability of the resonating structures. Now, the second golden rule, that is the second thumb rule that becomes a game changer, is resonance changes the bond length. Yes, the first is resonance increases the stability. The second is resonance changes the bond length. So how does this happen? Do you really want to know? Let's have a look, guys. Let's have a look. Let me give you an example. Okay, so my first example is, if I ask you in simple molecule, like let's say this is your acetic acid, CH3COOH. Okay, if I ask you, bache, let's say this is my oxygen A and this is my oxygen B. If I ask you what is the bond length between the COA and COB, if I ask you, bache, COA and COB, what is the bond length between the two? Then you would say, ma'am, the bond length COA wala is quite smaller than the B, right? Because this is a double bond and double bonds are usually shorter and the single bonds are usually longer. You would say that, ma'am, this is shorter and this is longer if my question is about the bond length. But basically what happens here is, guys, let's say this length, if you are saying that this length is different and this length is different. Now let me tell you the whole concept. If this is undergoing resonance, you can see that here the lone pair of electron over the oxygen will show the resonance. Okay, yes, so ultimately what can happen, the CH3COH and here we have O. So this lone pair will undergo like this. Let me show this to you. This will undergo like this and this bond will be broken like this. Ultimately, because of this resonance, now what can happen? Let's have a look. Let's have a look. ultimately we have to figure it out as O negative, and this will become a double bond, and here we will be getting a positive charge. Ultimately guys, because of this delocalization, because there is a resonance, now you cannot say that this bond is shorter, this bond is bigger. Now if you are saying that ma'am this is OA and this is also OB, now you see what has happened in this particular resonating structure. As per this particular, the second resonating structure, now you would say that ma'am COA is basically longer than the CO with the B, right? Because now it is getting a double bond, so it is getting shorter. Now your answer would be this. Now this bond is getting shorter and this bond is getting longer. Now guys, ultimately I could say that this is also wrong, this is also wrong. These two answers are absolutely wrong. Basically, then what is the correct answer? The correct answer is the bond length between both the oxygens are going to be the same, because ultimately here the electrons are undergoing delocalization from this to this. There is a delocalization, so because of this delocalization of electron, this COO bond length becomes equal. So if this is OA and this is OB, I would say that the COA is equals to CO B. The bond lengths are same. So this bond length and this bond length both are same. Okay, both are same. So if you are saying that this is smaller, this is larger, no, this is not so. So here we need to understand this with the point that resonance changes the bond length. Okay, now with this I can also explain this this particular thing with one more example. Okay, we have a very amazing example to explain the same thing. That is a very popular example also. Okay, that is, if you will see the structure of a benzene, this is the example number 2 I am taking on the same slide. So here if I am having a structure of benzene, if someone asks you, this is the carbon number 1, 2, 3, 4, 5 or 6, okay, and this is the resonating structure of a resonance. So whenever there will be a resonance, the atoms does not change their position, only these are the electrons that changes their position. Okay, so still atom will remain there only 1, 2, 3, 4, 5 and 6, only the electrons will move. So when there will be a delocalization of electron, we will be getting a double bond here, here and here. If someone asks you what is the bond length between the C1 and C2, now give your answer that what is the bond length, what is the bond length, what is the bond length between bond length of C1 and C2. Now here you will see that the bond length of C1 and C2 is greater, and here the bond length of C1 and C2 is smaller. But guys, if here you are saying that the bond length between C1 and C2 is L1 is equals to L1, and if you are saying that in structure 1, okay, let's say this is your structure 1, and the bond length between C1 and C2 is equals to L2. Now you would say, ma'am, this L2 is 2 in the structure 2. Then how would you determine the actual bond length? Then what is the actual bond length? The actual bond length between C1 and C2 can be determined by taking L1 plus L2 divided by 2. So it's better to take the average out of it. Okay, so if you need to determine it, because we know that these two are the resonance hybrid structure. So ultimately if this is 1, 2, 3, 4, 5, 6, there is a delocalization of electron. Okay, so ultimately the bond length between 1 and 2 and 1 and 2 is not greater or smaller, it is going to be the same. And that actual bond length between C1 and C2, we know that the C1 and C2 is going to be the same bond length. They will be having the same bond length. Okay, because these pi electron positions is not fixed, they are the delocalized pi electron. So ultimately the actual bond length between the C1 and C2 can be determined by taking the average. So basically आपको करना क्या है, what you need to do is just calculate the bond length between all the structures. This is L1, L2, L3, L4, L5, okay, and so on, if there are so many numbers, and divided by the number of resonating structures. Okay, that could be the formula. Okay, that is all the bond lengths divided by the number of resonating structures. number of resonating structures. That could be the way how you would be able to determine the actual bond length for a particular molecule. Okay, so this is your second rule, second game changer. Now we have a third game changer for the resonance. Resonance changes the bond order. How does it changes the bond order? Yes, absolutely. Yes, it just changes the bond order. So how does this happen? Let's see. Let's see, guys. Again, I can take the same example which I took right now for you. That is the example of a benzene. So if you will see the same example and you will see that this is C1 and C2 and this is the resonating structure of a benzene, which is this and this. These two are the resonating structures. This is the position 1, position 2, position 3, 4, 5, 6. I need to know between the only the position number 1 and 2. So here you would say that the bond order between the C1 and C2, bond order, let me write it again for you. If you would say that the bond order between C1 and C2 is equals to 1, and here for this particular structure you would say that the bond order between C1 and C2 is equals to 2. But in actual case there is a resonance, there is a delocalization of electron, and because of this delocalization of electron the bond order is not different for the different structures, it is going to be the same. So we can say that the bond order is not 1, the bond order is not 2, bond order is actually, actual bond order is equals to, if the first structure is saying the answer is 1, the second structure is saying the answer is 2, then we would say the number of resonating structures. How many number of resonating structures we have taken granted? Number of resonating structures. How many structures we have considered? 2. So we would say that 3 by 2. So ultimately this comes out to be 1.5. So this is your bond order between the C1 and C2. Okay, so this is the way how we can find out the bond order. Okay, so if someone says that the bond order is going to be the 1 here in this case and the bond order is going to be the 2, the answer is wrong, the actual bond order is 1.5, that is between the two. These are the canonical forms of benzene. Absolutely Purav. Okay, very nice bache. So we can have one more example to make you understand this if this doesn't help. That is the example number 2. So what is this example? Okay, let me take the example of a sulfides, that is SO3 2 negative. So when I draw the structure, I could say that this is S double bond O negative and this is O negative. Okay, the structure would be something like this. If I will be drawing its resonating structure, this could be coming out to be double bond O negative, or one more resonating structure which could be possible is S double bond O negative and O negative. So here in this case we could have the possibility of the 3 structures, 3 resonating structures, 1, 2, 3. So if I need to find out the actual bond order, now what will be the actual bond order between the SO bond? Actual bond order between the SO bonds, between the SO bond is equals to what? So when we have to find out the actual bond order, so what you need to do is, guys, it's very simple. Just figure out one of the sulfur oxygen atom. So here you can see that the bond order is 1, here you can see that the bond order is 2, and here you can see that the bond order is 1, right? So consider any of the one oxygen atom, fix it, okay, and then determine. So here the bond order is 1. In this particular structure between this sulfur and this oxygen bond, the bond order is 2, plus here in this particular structure the bond order is again 1, divided by number of resonating structures. How many resonating structures we have taken? How many number of resonating structures we have taken? That is 3. So this comes out to be 1 plus 2 plus 1 divided by 3. So this is 5 divided by 3, comes out to be 3.66, 1.66. So the answer comes out to be 4 divided by 3 or 1 plus 2 plus 1, that is 4. I did mistake, no, this has to be 4. Yes. that is 4 divided by 3. 4 divided by 3 comes out to be 1.33 something. Okay, so this is going to be your answer. Okay, so this is the actual bond order between the sulfur oxygen bond. Okay, so not necessarily that we will always be having the two resonating structures. We could have 2, 3, 5, 7, 8, 10. Okay, so whatever be the number of resonating structures doesn't matter. This is the way how you would be able to find out the bond order. Now if you don't know about the concept of resonance, your answer would be, ma'am, either 1 or 2, and this is going to be the wrong answer. So not the bond order is 1, not the bond order is 2, the right bond order is 1.33. So here we learn that resonance changes the bond order. Resonance changes the stability, resonance increases the stability, resonance changes the bond length, and resonance also changes the bond order. Is it clear to everybody? Okay, if there is any doubt, please do let me know. Yes, that's great. Okay, great Ansh. Hi Vipul. Hi to everyone, those who are joining me for this session. Now we are having another game changer rule, that is the dipole moment. Absolutely. So how does a dipole moment changes? Let me give you an example. Okay, you decide your own that how does it helps you. So here I am having an example for you guys, which is the example number 1. Let us take an example, then it becomes very easy for you to solve it. We do have a CH2 double bond CH single bond Cl. Okay, if you would see, and if I ask you what is the dipole moment for this particular molecule, if my question is what would be the dipole moment for this particular molecule, you simply answer. If I assume that you don't know the concept of resonance, then what would you answer? You would answer that, okay ma'am, this is carbon, this is chlorine, this is going to be partially positive, this is going to be partially negative. Here, because of the electronegativity difference, we will be having a dipole moment which would be something like this in this direction, and it is going to be mu1. Okay, so you would say that the dipole moment here is going to be mu1, right? Something like this you would say. And if I ask you, okay, what will happen bache in this particular structure, example number 2 here, it's not an example number 2 exactly, not an example number 2, just a slight variation. That is, if you would be having CH3, CH2 and Cl, again you would say, ma'am, here what I need to do is, this is the carbon, this is positive, this is negative, ultimately the dipole moment will be this, this is what you would answer. But guys, now what can happen? Here you were right, but here you are wrong. Why you are wrong? Because there is no resonance, so yes, you are absolutely right, there is no resonance, but here we do have a resonance. You can draw its resonating structure. See how? So this chlorine will undergo resonance like this, and this bond will be broken like this. So over the chlorine we will be getting a positive charge, and over this carbon we will be getting a negative charge. So here we do have a resonance, and if there is a resonance, how could you answer this? This is your wrong answer. So resonance changes the dipole moment. Let's see how. How does it changes the dipole moment? Now guys, see it carefully. Now you have put a negative charge over there, and this is your positive charge. So ultimately, where you did the movement of electron? The movement of electron you did from chlorine to carbon. That is from this to this, from this to this, from this chlorine to carbon. Here there was a movement of electron. So wherever there will be a movement of electron, that is the direction of the dipole moment. So initially you were saying this is the answer, but I am saying no, this is not the answer, this is the answer. So here, because of the resonance, the dipole moment is this, that is mu2. Magnitude also changes and the direction also changes. So here what has happened? The resonance changes the, we can say that resonance changes the dipole moment, changes the dipole moment, So ultimately, if you need to determine the dipole moment, how would you determine? Out of these two structures, how would you determine the dipole moment? because there are two possible structures. So if there are two possible structures, we can determine the dipole moment by a formula mu is equals to mu1 plus mu2. Okay, you can do the summation of the two dipole moments and you will be able to get your answer. Okay, so the dipole moment we can't determine by only this particular structure because they are in resonance, so we have to determine in such a way. Okay, so this is the point. Understood? So resonance changes your dipole moment. So whenever you have a resonance in any of the molecule, please be careful before answering all such questions. Now, an amazing and the last game changing role. Resonance changes the hybridization. So who all knows that? Right? Who all knows about it? Resonance changes the dipole moment. I hope my blue color is all visible to all of you. I believe yes, it is. Now resonance changes the hybridization. So how to understand this particular point? Let me give you an example and you will understand your own. Okay, so here I am having an example for you, which is C double bond C single bond NH2. Okay, so this is your molecule. This is CH2 and this is again, yeah, CH. Okay, so this is one structure, this is A, and here I am having another molecule like okay, so this much is fine, this much is fine. Okay, so you tell me what is the hybridization for this particular nitrogen. I need to know the hybridization of this particular nitrogen. So if this is my question, everybody would say, ma'am, okay, I can say that you would draw the structure, you would say that this is CH2 double bond CH single bond N, ma'am, over the N we have a lone pair of electron, this is hydrogen and this is hydrogen. Ultimately this is a tetrahedral kind of structure, right? And so therefore this particular nitrogen is sp3 hybridized. So this is what your answer used to be like, right? But I would say again this answer is wrong. Why this answer is wrong? Because you have not noticed the resonance which is happening. Is this lone pair free? No. Is this lone pair localized? No. This lone pair is undergoing resonance. So if this lone pair is undergoing resonance, then the hybridization changes. So how does it change? Let's have a look. This is CH2 negative CH double bond N, and then we will be having H2 and this will become positive. Now this is the structure. Now this is the structure, and if we would see this particular structure, what we can understand is, so what is the hybridization for this particular molecule? Guys, see, now you have a double bond, you have a hydrogen and hydrogen. So this is a trigonal planar geometry, and if this is a trigonal planar geometry, now the hybridization is said to be sp2 hybridized. sp2 hybridized. So is this answer right, that the answer is sp3 hybridized? No, the answer is not right, the answer is sp2. So what is the actual hybridization? Actual hybridization. So how you can determine the actual hybridization for a particular molecule? Guys, you know that these two are the resonating structures. If out of the two, if you would ask that which is the most stable structure, we know that always the resonance hybrid structure is the most stable. The resonance hybrid structure, let me draw the structure for you. Resonance hybrid NHH. So from this to this there is a resonance of a negative charge, that is the pi electrons. So there is a resonance. Okay, so if there is a resonance, so ultimately the actual hybridization is going to be between sp2 and sp3. So we would say that the actual hybridization is between sp2 and sp3, sp2 and sp3. So it would be between sp2 and sp3. So ultimately what I would conclude, guys, so here let me give you a conclusion about this particular thing, that is how resonance is a game changer. Resonance changes so many points. Okay, so let us conclude, and after that if you would have any of the doubt, please do let me know. Resonance always increases the stability, always increases the stability, increases stability. Okay, so the first point is about the stability. The second point is it changes the bond length. Resonance changes bond length. How could you determine the bond length? By the average. Okay, calculating the bond length of all the structures between that particular fixed atoms and then divided by the number of resonating structures. Third is it changes the bond order. It changes the bond order. Okay, that is the number of covalent bonds between the fixed atoms. Okay, fourth is changes the dipole moment. So whenever you have a question related to all such points, you need to be more careful. Okay, don't just answer by looking at a particular point. Look for if there is a resonance, it is going to be a game changer. It changes the hybridization. So these are the points. Changes hybridization. Now the question is, do we need to always find the average of all of the structures? Yes guys. So let me tell you, resonance hybrid structure is the most stable out of all. Resonance hybridized structure is the most stable out of all. If somehow the answer is not given in the options as per that, then you have to look for the more stable structure. So I would say that resonance hybrid is the most stable. Then after, you need to go through if there are 4 structures, and out of 4 structure, if any of the structure is most stable, you have to give your answer based on that particular stable structure. Okay, so resonance hybrid is the most stable structure. After the resonance hybrid, you please look for the most stable resonating structure. Out of all the resonating structures, the most stable resonating structure, and depending on that you give your answer. Okay, just like, let me give you an example. Many times what happens is, if there is a question for you, hybridization of nitrogen in CH2 double bond CH single bond NH2 is. Okay, this would be the question. The options are sp2, and then the question says it is sp3, the question says this is sp3d, or the option says this is between sp2 and sp3. Then what would be your answer? Of course, we know that the resonance hybrid is the most stable structure. Okay, and there is a resonance, so the hybridization could neither be sp3 because of the tetrahedral geometry. Here you can see that this is a tetrahedral geometry, and here this is a trigonal planar geometry. So this could not be sp3 because of the tetrahedral structure. Now there is a resonance and it will become trigonal planar, so this could not be sp2. So what is the right answer? Between sp2 and sp3. So this would be the right answer. But sometimes what happens, you will be given with options like sp2, sp3, c, sp3d, or let's say d, sp3d2. Then what would be your answer? You are not given with such an option. Now what would you do? None of these is not also there. Then sp2, sp3, sp3d and sp3d2. Now depending on what particular structure you will be answering. Now you have to see out of the structure number 1 and out of the structure number 2. So out of these 2 resonating structures, which is the most stable one? So if you will compare between the 1 and 2, you will find that the first structure, this is more stable because this is neutral and its octet is complete. So the first is most stable. So if the first is most stable, your answer would be as per the structure number 1. Okay, so as I said, hybrid is the most stable. Then after, whatever would be the number of resonating structures you are given with, look for the most stable one, and depending upon the most stable one, give your answer. Okay, so here my answer would be like sp3. So if these are the options, mark this as an answer. If these are the options, mark this as an answer. Okay, so this is the way, this is the pattern where you need to understand that resonance plays a very important role. Okay, so thank you so much guys. If you really like this session and you learn through it, then please hit like and do share it with your friends, and don't forget to follow me on an academy. I am regularly bringing so much effective and like valuable sessions for you that are going to put a lot of weightage in the JEE Mains paper this year or the upcoming years. So don't miss them out. Do follow me on an academy and keep learning, start learning. Okay, so don't forget to click over the follow button. This is it guys. Thank you so much. We'll see you in my another session which is going to be on aromaticity. Let's have a look.